In this example, we are going to use the integrated fuselage wing model that you see here on the screen to show you how to analyze or set up and analyze edge joints for either bonded or fastened joint applications. We're going to focus this example on the fastened joints. You can see the large integrated fuselage wing here. Kind of get a sense for how large this is. I can have my little spaceman. Gives me a little sense of scale there. So it's a fairly large commercial aircraft type application. And what you're seeing on the screen now are zones, sizing zones, as you're probably very familiar with at this point. I can change what how I'm coloring now to structure. And so basically the structures are indicating the areas where you would have fabrication joints or splice joints, splicing together large structural assemblies together. And so I'm going to focus on the center fuselage to outer fuselage splice locations in this example. And what I need to do is create an entity called a joint at these locations. But just so we're all kind of on the same page here, these would be edge of structure boundaries and would kind of indicate locations where, let's say if you had plies, that your plies are not contiguous or not continuous across that boundary. So in this scenario, I can show cuts. Go into this boundary here, and you can see indeed we have basically a location where the plies are not continuous there, as well as over here. So we would need some sort of splice joint to splice these skins together. Splice away. And to create a joint, it's fairly simple. First, we basically just need to select boundaries. And when I turn on my select boundaries, it's basically showing me all of my zone intersections that I have available to select. And I can select a few of these. Right-click, select Create Joint. And we have this membership shown, one member versus two member. And then the first and second member are displayed with these colors. What does that mean? So if I turn off the second member, now I see only a one-sided joint. So what's the implication of that? Well, it has to do with how the loads are processed and the assumption for if the skin is continuous or discontinuous over that joint. So a one-member joint would be, the assumption here would be a discontinuous skin. So in essence what we have, which is a skin splice over top of a frame. And the idea with it being one member, that indicates that the loads that we use to analyze each side are basically coming from one member, where we take the entirety of the load that's transverse to the joint direction, as well as the shear load along that edge, and we root sum square that to determine the total bearing force transfer. The assumption is all the load in the skin has to transfer down through the frame, back up into the other skin through bearing. And then our bypass load direction would be along the length of the fastener pattern. Compared to a two-member joint, would take loads from both sides of the joint and would do basically a differential in XY across that fastener pattern to determine the load that's being transferred from the skin or essentially taken out of the skin and transferred through the cap of the frame. So to set up and analyze a splice joint, we are going to set up back-to-back one-member joints. So that's easy to do. I'm just going to go ahead and create this one side. And then there's our joint. You can see that the direction of the arrow indicates the pull-off direction for the edge joint. And now I can go back and I can create another set of joints. I can make these also one member, and then I can flip the orientation of those. There we are. As you can see, I have one side of the joint of the splice has a row of joints, edge joints, and the other side has a row of edge joints as well. And now these are entities that we can assign a joint design, a load property, and analysis property to, and then they will also be able to report margins of safety and hold analysis results and analysis details to be able to display and report those on the joint themselves. So I've gone ahead, fast forwarded a little bit, and created those joints at the structure boundaries, both the splice locations to the center fuselage, and I can switch back to coloring by any, which is basically going to color by zone, or I can color by joint to highlight just those sections. And now, just like any panel or beam type structure, in HyperX we can assign the three properties that are required to run analysis. And the first being a design property. I'm going to take a quick peek at this design property. We're going to start with a single shear assumption on each side of the splice. The underlying plate is going to be an aluminum 7050. However, we will first and foremost inherit the laminates from the acreage sizing. We will inherit those at each location, and then also inherit the thickness, so ply count of the laminate. And we're going to assign an HL11 fastener spec. So that would be the, take a quick peek in our table here. HL11 is a -8, so that's a 1/4 inch fastener. The dash numbers indicating, of course, the shank diameter. It is a countersunk head fastener, so 100-degree countersink, and then the corresponding shear and tension allowables being displayed here. And these are double shear allowables, so we will knock those in half each time that we analyze a single shear joint. A couple things to note here about the fastener definition. We are referencing a bolt material. It's a titanium fastener. The reason we do that is to get the temperature knockdown. So if we've applied an analysis temperature on a design case, or the software has imported elements and or nodal temperatures, we are going to knock down the corresponding shear and ultimate allowables using the FTU and FSU knockdowns respectively from the bolt material, the temperature knockdowns that are assigned to that bolt material. All right, so we go ahead and apply. Notice that I've got a specified fastener spacing and a number of rows. That's constant at this point. Those get assigned to the joints just like you would assign a design to a panel, drag and drop, or right-click and assign a visible selection is also an option. I'm going to use an element-based load processing technique that I have. So what that means is each one of these elements at each joint location, it's going to do an element-based processing and run margins for every single design case at every single element. And then lastly, we want to use a joint analysis property that I have set up already. This has two failure modes. The first failure mode is a fastener specific failure mode. It has fastener tension, shear, tension shear interaction, and then all of the bearing for the underlying metal plate. We've got all of the inputs here, as well as we're doing a couple things here where we're deriving fastener bending, and we are computing a prying force based on the heel toe from the eccentricity that comes from the shear offsets of the plates. So this is kind of using the approach documented in the Macomb supplement of Brune, where the bending is derived, even with an edge joint, is derived from the shear offset of the composite to the plate, and then an overturning bolt moment is computed, and then that's used to derive the bolt prying force from the heel toe effect. And then we also are analyzing this for bearing bypass. And bearing bypass analysis is likely going to be fairly critical. Let's see. I'm going to go ahead and size this. Okay. And I can take a quick peek at the margins of safety. All right, so by inheriting the thickness of the laminates attached to it and writing margins for the bolt and bearing bypass, I can see I have quite a few negative margins. Controlling criterion is, of course, as I mentioned before, bearing bypass for pretty much all of it, which is not a surprise. Bearing bypass is going to be pretty much your critical shear method. If you're fastener shear critical, you've really got a problem. So what does that mean, bearing bypass? What's informing this method? We go to the composite material that's being referenced by the laminates and take a quick peek at the the bearing bypass envelope here. So I can see this is the allowable that is informing my analysis. You can see on the x-axis we have bypass stress. On the y-axis we have bearing stress. So we have a negative portion where you have compression bypass, and the tension portion, we have tension bypass, and the bearing stress cutoff here being about 75 KSI. This is further adjusted using the correction curves that we have. Try that go away. Down here. And we have corrections. In this case, we have bearing corrections being applied as a table. And what we can see is we have multivariable correction tables, the correction factor being this last column. And then we have two independent variables. We have to define one as what we call the interpolated variable, which then sits on the x-axis of this chart. So we interpolate between those values, and then we have multiple curves that are a function of ply percentage. So as your %45 degree plies changes within your laminate, you jump to different curves. Okay, so this may look very similar to your correction curves that you would see in your stress manuals and material definitions. So we have the ability to correct the bearing and bypass allowables with a whole slew of different dependencies and variables, spacing, S over D, thickness, diameter, and so on. All right, so let's now try to resolve these negative margins. Well, what if I just wanted to say change the edge band thickness, and I just wanted to set that? Well, I can do that very easily in my joint design property. Go back in, and instead of inheriting my laminate thicknesses for the laminates that I'm connected to, I could say select laminate, and I could just grab one out of my laminate library here. Select OK. And so now what I've done is I've said at every joint we have a 17 ply edge band that's built up at the joint interface, and that does not have to be represented at all in the gross acreage sizing. It's just for analysis for joint margins. And I can see once I reanalyze that after that change, what is the impact to the margins. And we can see the impact to the margins. All right, well, still negative, quite negative. So that's not going to cut it, just a single edge band thickness. So what I'm going to do now is I'm going to put this into sizing mode. Not only sizing mode, I'm going to put it into advanced sizing mode. And this allows me to make a bunch of selections here on my edge band thickness. And I can add in a lot of all of these materials now. Okay, so now I'm going to have it cycle between 17, 18, 19, 20, 21, 22 ply edge bands. I'm also going to let it change my fastener selection. So I've got multiple fasteners. I can put multiple fasteners here by changing that from selection to selections. I'm going to add in, let's say, an HL10-8, and maybe I want it to try an HL10. Let's try an HL10-10. Okay. I'm going to let the spacing vary, and I'm going to let the number of rows also vary. And notice that the order tells it to start at the higher spacing and work its way down. Up arrow is telling it to start at a lower number of rows and work its way up. And then I can be very explicit as far as to how I want it to change these parameters to try to find designs that generate positive margin. So let's say the last thing I want it to do is change the thickness. So that would be the last priority. The first thing I want it to do is change the spacing. The second thing I want it to try to do is add another row. The third thing I want it to do is try another fastener. And the very last thing to do would be try a thicker edge band. And then that defines my order of operations for sizing. And then I can resize all of these. And now I have all positive margin. And just like if I were doing sizing with panels, I can say, well, what are my low margins? I can select this in the legend. I can open the analysis watch window or the analysis results watch window. Let's try that again. There we are. So these can also be recorded in the window. I can sort these. I can say, yep, in fact, bearing bypass is still critical, still controlling, which I would have guessed. So that's not surprising to me. And so, yeah, you still have all the reporting capability for edge joints that you do for panels and beams, as well as the ability to locally size these in such a way that you can size the joint with a coarse finite element model, and you can override the thicknesses of the edge bands, and then you can extract the corresponding sizing results. So this will tell you what the fasteners are, which fastener spec has been used in which location. Where did we need the I hit a protruding head there. So I have a protruding head and a 100-degree flush head. I probably should have done an HL11 here to do countersink in the skin, but get the idea where we needed the larger fastener to show positive margin. We can see where we have, say, number of rows. So the spacing here, you can show the pitch of the fasteners. You can see the number of rows required, where we needed 2 rows versus where would one row work on each side. Looks pretty much like you need at least 2 rows on each side, and that's not unusual for splice joints to have 2 rows on each side of fairly large fasteners. And lastly, you can see the thicknesses. So the edge band thicknesses, where we needed to build up thickness to pass bearing bypass, and kind of makes sense where you have a lot of load transfer across, right here near the wing or carry through locations, where the load transfer across those joints is pretty high compared to up here at the top of the fuselage. All right, well, that's the end of this demonstration.